Good morning, everyone. Glad to be here to share our recent work on camera-centric understanding and generation. So this is mainly done by my research fellow Liao Kang, the handsome guy over there, and with collaboration with Science Time, University of Michigan, and MPI. So my name is Chen. You can call me Kevin. So yeah. The problem we want to solve here first is to generate images with rich camera language. We know that camera language is very important to express our feeling and our interpretation of the scenes. For example, like the one in like Inception movie and the one in the Jaws. So this is called Dutch angle. Yeah, so we basically need to adjust the raw angle of the camera to express this kind of scenes. And if you try assisting generation model and you want to introduce this kind of camera language into your generation, this can be very challenging in that when you put your camera parameters into the text prompt, like 20 degrees of RAW and 35 millimeter of lens, that kind of numerical parameters will usually be neglected in your text prompt during the generation. So for example, if you look at the long shot focal length, you basically do not see any differences between these two generations. That's the first problem we want to address. And the second problem we want to address is whether we can, at the same time, achieve accurate understanding of the camera geometry from the images. This is a classical problem where we need geometry understanding for camera calibration and post-estimation for many other downstream applications. There are many methods to achieve that, but mostly focus on low or mid-level representations. For example, you can train a model to regress camera parameters from input images, or you can use intermediate representations or dense geometry fields like the distortion maps or camera rays or perspective fields to bridge the prediction gap, to make the parameter prediction more accurate. But it happens that given some images that are like with poor structure, very poor texture, this can be challenging in that to predict accurate parameters, you need to capture holistic and coherent spatial concept for that. So we are asking whether we can address these two problems in a unified framework. In that most assessing studies, they basically address this problem in isolation. There are many works performing understanding of camera geometry from images. On the other hand, there are a lot of works that try to introduce camera geometry as condition for image or video generation. Either camera intrinsic for controllable generation or using camera extrinsic to move the cameras around to generate nice videos. But we feel that these two problems are interrelated in the sense that they share some complementary representation. So when you go from understanding to generation, you basically need to encode the geometry to control the visual content. When you go from generation to understanding, you basically need to decode the camera geometry from the world and do the understanding. So we are asking whether we could kind of have a way to combine these two problems together and solve them in a unified framework. And basically, you can think about that, we can use large language, large multimodal models to solve that, because these models basically can already perform understanding and generation in a single unified model, like the very nice work of Bagel or GenX Pro. Basically, you can do very nice generation. At the same time, you can do very comprehensive understanding given images. But then you will see that most of this work basically assume simple camera setting where it is confined to the front view and cost focal length. Yeah, partly due to the data that these studies collected, they have to be kind of from photographers or from amateurs. They are mostly limited to horizontal latitude and frontal view. So that limits the capabilities of these models to generalize to more kind of extreme camera geometry. The main contribution of our work here is to design a way to interpret the camera as language, yeah, instead of like numerical numbers. First thing we do here is that we try to construct a large-scale data set called puffin. Yeah, puffin is the name of the bird over there. Yeah, basically it's a large-scale data set of 4 million vision language camera throughput spanning diverse indoor and outdoor scenes. And later I will introduce more about the data. In addition, we also established a benchmark for evaluating the camera-centric multimodal models. And with the data, we can train a model, a unified model, basically to treat camera geometry as the first-class modality rather than supplements or conditions. And model together with vision and language and also share the same reasoning chain of thought pipeline. And to basically, in other words, yeah, we want the model could perform reasoning and thinking to bridge the modality gap between camera and vision language. That would allow us to perform better spatial reasoning and also enable many different applications. For example, we can, with our model, we can now understanding the geometry of the images. This is to illustrate the perspective field with the latitude and also the up vector. We can accurately understand the geometry given the images. And at the same time, we can also generate images with different geometry. For example, with a very skilled latitude and also different FOV. And with some further instruction tuning, the model can be used for world exploration. Yeah, like the SD, the up, down, left, right. Yeah, we can kind of convert this camera geometry into some action as condition to generate different views of the images given a reference view. And we can also perform some spatial imagination and also photographic guidance. Okay, in terms of method, we basically need to solve a few challenges. It's not entirely new, but we found that the solutions we propose are important to enable this kind of camera-centric framework. Yeah, first, we asked the question whether we can train existing LMMs like Chen or Intern VL to capture camera parameters accurately. We found that this is challenging in the sense that existing vision encoders for LMMs, they mostly capture, like they can capture accurate kind of the semantic meanings, but they could not generalize well to like capturing accurate geometrical details that can be used for grounding or text-to-image retrieval, but not for the task we are targeting here. So our experience is that we need to choose a suitable vision encoder before we fed the representation to our MMM. What we are doing here is that we try to choose the visual encoder proposed by the two following papers, Radio V 2.5, that's distilled from both semantic and vision-centric teachers like Dino V2, Clip, and Sam. And this vision encoder can be further aligned and fine-tuned to work well with our targeted LLM to provide the needed features to understand to encode the imagery, the geometric details. That's the first thing that we address here. And the second challenge, as I mentioned earlier, the camera parameters are usually too numerical to be understood by the LLMs. For example, the RAW, the pitch, the yaw, and the FOV. So how to make them less easy to be forgotten by or neglected by the LLM. And in the way we try to solve that, especially for the generation part, is to encode these camera parameters into perspective field or camera map. The notion of perspective field is proposed by Lin Yijin, also the co-author of our work here. This was proposed back in CVPR 2023. This is a very nice representation that we could use as a condition for camera geometry. That you basically encode per pixel, dense per pixel information about the camera view using the arc vector and also the latitude value. So you could see that the arc vector over here basically can be explained by many vertical edges of the figures. And the latitude, the fact that the latitude of above the horizontal line being positive and below being negative, they have strong correlation with the local image features. And that kind of serve as a strong condition that could be used to control the generation with the desired geometry. So the way we try to make use of this perspective field or camera map is through training a camera map tokenizer. In fact, we can use the VAE encoder to do this, to process this camera map, because the map itself has 3 channels. We can treat it like an image. And then we can encode it into some camera latent and then fit it into our model. So these are the 2 main mechanisms that we introduce here. The solution is pretty simple. We can actually make use of existing LLM framework. For example, for our LLM, we use the Queen 2.5, and also the diffusion model, we use SD3. The way we connect the 2 models together is to the through a connector. It's a 6 layer transformers with some nullable queries. And to introduce the better vision encoder, we use the method that I mentioned earlier, which is distilled from the semantic and also geometry teachers. And for the camera map, we introduce at the generation branch that serve as the input to the diffusion model together with the noise input. And here we also have a camera parameter tokenizer that tokenize the camera parameters into some camera tokens to fit into our LLM. So this is a very basic framework that we built on top of existing model. So to understand camera geometry, you basically just need to provide a test prompt, say describe this image in detail and predict the camera parameters, then it can generate the text that provides you with the geometry information. And to generate the image, basically, you just need to describe the image appearance that you want, supplemented by the camera parameters and the camera map. And this camera map can be readily obtained by converting the camera parameters into the camera map. So we found that doing that itself is not sufficient because the modality gap is still there. The geometry understanding is still lacking somehow. So we try to improve that by enable the model to perform some thinking, as in assisting LLM. We do chain of thought, but here what we do is that we try to perform the chain of thought, the thinking, by decoupling our geometric context into more kind of fine-grained dimension. For example, into the row, into the pitch, and also FOV. And then we perform the reasoning for each of these dimensions separately. Highlighted by the green tags, the red tags, and the yellow tags over there before the model produced the final answers. So we found that by having these thinking steps is crucial to get accurate parameter estimation, because by doing that, we can establish connections, very good connections between the spatial visual cues and also in the geometric, the camera geometry. One thing we kind of introduce here, I think this is interesting, is that to share the common thinking pipeline as in the language, we try to relate the geometry, the parameters, camera parameters, with different photographic terms. When photographer, when they shoot movies or when they shoot take photos, they basically try to use different kind of terms, professional photographic terms. For example, at the images over there, when you have different roll angle of the capturing angle, so they call it Dutch angle. So either counterclockwise Dutch angle or clockwise Dutch angle. And for pitch, you have also different language to explain that. Is it a small tilt up, large tilt up, or on shot or tilt down? And FOV, you have close up, medium shot, wide angle, ultra wide angle. And we can actually translate our camera parameters into this language so that it can be better understood by the LMM models, and also draw better prior, to make use of the prior encapsulated in the large multimodal model. So what we did here is that we define every term with a specific bin of in terms of the angular angles to fit different terms. Then we can perform thinking with camera. So this is an example of doing the inference using our trained model. You can see that with that particular input, the thinking process can accurately provide the answers from the thinking process, like the roll angle. It explains as a small counterclockwise Dutch angle by looking at the visual features of the image, being slight diagonal alignment of the cobblestone pattern and the parked cars. And for the tilt down, which is more difficult, you try to look at the horizontal line, being slightly above the center of the image, and also FOV as well, being ultra wide angle because there's an expansive view of the cobblestone area, the trees and the surrounding buildings. And here are a few more examples that basically show that the model is capable of getting the camera parameters through looking at the different visual cues or visual features of the images. Okay, so we can't do that without collecting a data set because there isn't any large-scale vision language camera data out there for us to train our model. The Puffin4M dataset construction is given in this figure. It's a bit complicated, but it can be generally understood as 4 stages. So first, we need to collect a lot of panoramic data that can be collected from like existing data sets as well as YouTube data from Google Street View. We need to do some adjustment or some correction to the data. And then we can introduce a virtual camera to generate the perspective image following, we use a pinhole camera model to generate those kinds of perspective images. And then with the perspective image, we can generate the scene's caption using VLM and further polished by a larger LLM to get refined caption. And with the camera parameters that we can define, we use the photographic terms to explain these camera parameters into different terms like this. And also we convert these parameters into camera maps. And together, we send them to VLM to get the spatial reasoning data that we could use to train the thinking process of the model. So the panoramic data can be collected from many sources. We collected quite a lot of them, almost 200K of high quality 360 degrees of data from YouTube. You can actually get a lot of these YouTube videos that features panoramic scenes. And they're mostly 4K and some of them up to 10K of resolution. Collected both indoor, outdoors, and across many different countries to improve diversity. We need to do some cleaning of the data before we can use them to train our model. First is to perform horizon alignment because some of them, they are not really aligned with the horizontal line. With some vanishing point estimation, we can correct the horizontal level of the image so that we have a better, we can capture more accurate perspective images. And some of them, they have a large portion of them featuring like the cars itself, rather than the scenes. So we need to manually narrow down the valid observation scope so that we can retain the scenes rather than the redundant areas. And with that clean data, then we can capture a lot of images with a standard view, with the pitch, roll, and FOV variants. Okay, so let me show some results. We divided into two parts. One is camera understanding, another is camera control generation. So for camera understanding, we compare with different methods, including those vision-based and learning-based method. The one called jaw calibration, yeah, that was the paper published last year, and that represent the state of the art. You can see that our method with the thinking process and the joint understanding and generation modeling, yeah, we can perform very well in terms of the row pitch modeling as well as the FOV modeling. That's the median arrow, lower is better, and that's the area under the curve given different thresholds, higher is better. One thing we observe is that is estimating pitch, yeah, basically the up and down, and FOV is more challenging than estimating row over here, because the row estimation can be better supported by the visual features that we can find in the scenes, because you have the floor, you have all these buildings that basically implicitly tell you the row angle. But estimation of pitch and FOV require more extensive contextual priors and visual features to tell you about the result. We found that rich spatially contextual knowledge in LM helped. Yeah, so the unified modeling is useful. Here are some qualitative results. We show the horizon line, which is the 0-degree latitude, by drawing different colors of line for different methods. The red line is the ground truth, and our method is shown as green light. In most cases, our method performs pretty well in comparison to the other two algorithms. JAW-CapLab is a vision-based method, state-of-the-art method for geometry estimation. And here I visualize the camera map, visualize the camera map or perspective field. You can see that from the latitude and also the up vector, we can observe that most of them make quite a lot of sense and quite pretty accurate. Yeah. The next thing we do is that to to measure the performance of different generative model for camera control generation. We compare with contemporary methods, including like GPT-4o, Quinn, and NanoBanana, and also PreciseCam, published in CVPR this year. We measure them against the arrow in up vector, latitude, also gravity. There are like two different versions over here. They differ in terms of the text prompt that we provided to this method. One is with degrees and another one is with photographic terms following our setting. And because, I mean, they generate images without the camera parameters, so we have to use a vision-based method, the JAW-CapLab, to estimate for the pixel-wise camera mapped so that we can perform a fair comparison. So you can see that our method performed very well in comparison to all these assisting methods, because we included more explicit camera map as our condition for the generation. Yeah, another way to look at it is by plotting the different, plotting the prediction of row, pitch, and FOV versus the ground truth. The method is more accurate when the predictions align at this x equal to y as is. Yeah. So as can be observed, yeah, our method provided results, produced results better than existing generative model. And interestingly, we found that the role estimation, yeah, is kind of difficult for existing models to learn. In that you can see that most predictions are horizontal instead of aligning with this red axis over here. Because for this baseline, they basically train on dataset with bias that prefer near level shots. So they have problem estimating, problem generating images with different row angles. Yeah. That's the observation. And here are some qualitative results. Basically provide the caption, yeah, together with the camera parameters to all these methods and let them to generate the image and use the method published last year, yeah, the GeoCatlib to get the camera map together with the confidence. We can see that most existing method, yeah, they get a larger error compared to ours, and that shows the importance of using better condition, yeah, for the camera geometry. Ablation study. I think the key message here is that we show thinking with camera is important. Compared to our own method without thinking. Yeah, with the thinking process, we can improve the geometry understanding performance a lot. And this shows an example, yeah, without thinking and with thinking. You can see that the camera map generated, the arrow map generated, yeah, the error is much reduced and the image generated is much aligned with the description provided. And with and without camera map, the generated images tends to be kind of erroneous. It doesn't follow the exact condition that we provided, but with camera map as a stronger condition, that regularize how the generation process, regularize the generation process. I think a common question is that single task versus unified training. When we train both generation and understanding together, did we observe any benefit by unified training? In our problem, we did observe some improvement in both tasks. For camera understanding, unified is better than training in isolation, in the sense that the diffusion loss actually that we use during the generation training, it actually helped to enhance the geometric perception. As you can see, this higher is better, so unified training is better than training in isolation, and this is lower is better, so unified is better than single task training. For generation, we also observe unified is better than training in isolation, but it is less pronounced here as compared to the chart that we show here. But we do see that generation improve, especially for more challenging scenarios like field of view estimation. Yeah, that basically requires more holistic understanding of the image to do well. So geometric understanding helped in this case. Okay, in terms of applications, we can perform some instruction tuning to enable more applications like world exploration, spatial imagination, and photographic guidance. This is world exploration, where we provide an initial view given by the red box, yeah, the red highlighted image over here, and the camera geometry with different yaw angle to generate a new image. Yeah, that is basically in the same scenes but looking at different angle. So with that, yeah, we can use, for example, VGGT to construct the scenes, and that basically give a more holistic view of the scenes that we are exploring. These are all generated by the Puffin model. Yeah. And another few examples over here, not just for outdoors, but also for indoor scenes. Some examples that we basically change the yaw angle from left to right based on the center reference image. You can see that it's pretty nice, and we can kind of use VGGT to build a 3D model for 3D construction based on this set of images. We can perform spatial imagination as well. So here, we basically just need to provide the image and camera geometry, let the model to imagine for the text and use the text to generate the images. For example, given this view, I can ask the model to imagine the scenes extending to your right, and the imaginations rates are these. Okay, that would be a cozy kitchen with cabinets, with windows illuminated by warm lighting, basically following closely to the given view. And those images are generated using the same model, yeah, based on the imagination. You can see that it's not too far away from the ground truth we have here. And this is another example. Yeah, we asked the model to imagine the scenes behind this perspective view. And it says that there would be a TV and a wooden stand, and there would be dining area visible through the open doorway. So all these images are generated using the same model, and it's kind of aligned with the ground truth. And another application that we try is that photographic guidance. Sometimes when an amateur take photos, they don't know where to point to and how to adjust the position of the camera. So the view tends to be poorly composed. What we did here is that we collected some data sets with aesthetic scores and fine-tune kind of our model using instruction tuning. Here, basically, you just need to give the image, original image as input with the prompt, guide me to take a better photo with higher photographic aesthetics. And the model will be able to suggest your angle and pitch angle that you need to move your camera so that you can get a better composition. Yeah, so here, basically, you can see that like from this input, yeah, it will suggest you to move up a little bit, and then you can change the yaw a little bit so that you can take a better image with better composition. Yeah, I think this is some interesting application that we try. Okay, so the method comes with quite a number of limitations. First is the camera model that we assume. It assumes a pinhole camera model, so it doesn't capture radial distortion and also more complex length aberration. And the other limitation is that we haven't done it very well to maintain the consistency. If basically the consistency is enforced between the initial view with the generated view, but not among the generated views. So if we move too far away from the initial view, then the generated views might look different among them. Yeah, for example, there's a pillar here, but here we don't. So we can solve that maybe by using more constraints in terms of the during the generation, by using epipolar geometry or using better positional encoding. Okay, so this is the last slide of my slide. Basically, we give the name of the method as puffin because puffin is a lovely bird that can fly in the sky and swim in the sea, so it's versatile. And the eyes is wide angle autofocus eyes, so kind of represent the nicely camera geometry that we want to encode in our model. So the take-home message is that camera can be treated as a reasoning modality if you treat it as a language and you project it to photographic terms. And we can unify camera-centered understanding and generation, and that allows our model to reason about the space more in a better way and more interactively. We hope that we can achieve more robust spatial intelligence this way, and future work includes currently we have the model standing on a static position, moving around. We really want to do this as continuous and really can have other dimensions like go deep into the scenes to enable camera-aware world models. So yeah, we have other related works, basically training causal transformers to accept streaming input images and perform incremental 3D reconstructions, and that's relevant to our work over here. And we maybe combine them one day. Yeah. So that's the final slide of my talk. Thank you. Thank you.
Okay, thank you for the great talk. Any questions? Yeah, you can use the mic in front of you.
Hello, Professor Chen. I think this is an interesting topic, especially it's very important for let's really reconstruction or generation. And I have a question, maybe a little bit out of scope. I'm not sure. Do you think like in videos containing like motion trajectories, like a human motion or whatever, like birds flying or whatever, do you think it's important to disentangle like motion trajectory from the camera trajectory? Because I like empirically, I think the motion will affect the prediction of camera parameters. So my question is, do you think it's an important task to disentangle the motion from the camera trajectory, or you think it's just trivial? It's not important. So what's your opinion on this? Because I'm very interested in such topic.
Yeah, so in our current framework, we don't consider dynamic objects. So yeah, surely, I mean, disentangling them is important if you want to train your model well, yeah, with good performance. And dynamic objects basically add another level of like difficulties in terms of modeling because the motion, yeah, is very different and yeah, add complexity to the training. We haven't explored that, but yeah, definitely when we want to scale up the model with more data, we need to use those data sets. That's something that we need to consider. Yeah.
Okay, thank you.